move on to my presentation about black holes. Great. So today we're going to talk about black holes and why recently they've been so much around social media, popular content, and what's the general big fuss about black holes. And to introduce myself a little bit and tell you why I might actually be capable of telling you something about black holes in the first place, let me tell you that, first of all, my name is Aisha, so hi. Great to meet you. I'm an extragalactic astronomer, and what that means is that I do look at the universe in my professional work as a PhD student. That's work. I look at the universe beyond our own Milky Way. And to be more precise, if can you see my cursor? That might not be the case, but I hope you do. In case you don't, I'll have a laser pointer. That's even better. So if we look at the present day, what I mean by extragalactic astronomy research in the local universe, if that's the present day, then I look back roughly 4 billion years back in time, which corresponds to redshift of roughly 0.1 for those of us who do speak redshift. And in particular, I look at galaxies, which are large collections of gas, stars, and dust held together through a gravitational potential. And out of the galaxies themselves, I'm particularly interested in the supermassive black holes residing at their centers and how they influence the evolution of their hosts. So now that I hope you know that I may know a thing or two about black holes, let me tell you what we're going to talk about today. I've divided the talk into 3 parts, so in case there is any part that you already know and want to skip, you'll be able to identify it by little circular icons that will pop up in the top left corner of each slide. First of all, I'll tell you what black holes are so that we're all on the same page. Then we'll move on to discussing how and why they won the 2020 Nobel Prize. And finally, I'll tell you about the subject that interests me most, which is why should we at all care? So let me set the stage with answering the question of what a black hole is. Now, these are, let's be aware of the fact that these are the most exotic and at the same time most simplistic objects, mathematically simple objects in the universe that we know of. So in order to understand them well, we need to do a quick general relativity recap. And I'm going to use a couple of equations in my slides. Don't worry, they're not, the full understanding of the mathematical expressions is not relevant. What I want you to take away from those equations is to have a, if you will, a mathematical feel or understanding for all the background I'm telling you about. So if you look at the beautiful tensor form of general relativistic equations, what they really mean is that Einstein came along and said there is an equality sign between the curvature of space-time and distribution of mass. So we can no longer think of gravity as a force in a Newtonian sense. We cannot think of it as this spooky action at a distance held by invisible interaction medium. Now, gravity is a demonstration of how our 3 + 1 dimensional space is curved. Now, as much as it sounds awkward, let me illustrate that in 2 dimensions, because that's as much as I can do on screen. If you have no mass in the general relativistic universe, space-time is flat. When some mass arrives, just like the sun, the Earth orbiting around it, we see that the space-time begins to curve, and the Earth, this tiny dot around the sun, will run around in ellipses around the sun just because it follows a straight path in a curved space-time. So as much as this illustration is maybe visually pleasing, maybe a little bit funny, the effect of bending the effect of curvature of space-time on things like light has already been proved, fantastically well by experiments we performed on, for example, solar eclipses. So the experiment conducted by Sir Eddington back in the 50s, 40s, if I remember correctly, required a solar eclipse and a light directly behind the sun. On a regular day, you wouldn't be able to see a star right behind the sun, not only because the sun is bright, even if the sun was dark, we wouldn't be able to see it because it would block our way. But because the space-time is curved, the light was bent around the sun and made it all the way to the Earth. So in this perspective, say the star is here where my pointer is, and then it would get bent and transfer to the Earth. And that's exactly what we saw in the solar eclipse experiment. So the curvature is easily measurable, if you will, if we have close enough objects and good enough observable conditions. But how does it tie into black holes? Well, you've seen that stars, massive celestial bodies like stars and planets, do bend the space-time a little bit. But what black holes do, they bend it to infinity, if you will, because black hole is this exotic object which has a point of infinite density at its center, enshrouded in a boundary of no return we call the event horizon. Great. So now I would like to, if there is anything I'd like you to take away from this talk, is a correct definition of what a black hole is, because I know there are many around social media that might be misleading. So a black hole is an object so massive and compact that even the light cannot escape its gravitational potential well. And it is key that it has to be massive and compact at the same time, because there are objects in the universe that are much more massive than black holes, and yet they are not enshrouded in event horizons, like the largest structures in the universe, clusters of galaxies, which hold millions of billion, well, they call several billions of solar mass invisible matter, or even several orders of magnitude more than that, but they are not covered in event horizons because the distribution of matter is not compact enough. So how compact is compact enough? Well, again, an equation which tells you what is the radius at which we are expected to find an event horizon from the center of the black hole for a solution of spherically symmetric, non-rotating spacetime, essentially the easiest black hole we can think of. So as you can tell, there are a couple of constants in there, the gravitational constant g, the speed of light c, but most importantly, radius is directly proportional to the mass within the event horizon, and inversely proportional to the square of the speed of light, which is a gigantic number, 10 to the 8 meters per second. So I know it doesn't tell us much right off the bat, but let me bring this together with some more familiar examples. So if we look at the objects closest to us that we're aware of, for example, the sun, it has the mass of 10 to the 30 kilograms. And I would like you to remember that number and have it at the back of your head, because from now on, I will mostly be referring to astronomical things in terms of solar masses. So 10 to the 31 followed by 30 zeros, that's the mass of our sun, which is roughly 1 million times more than the mass of the Earth. And all of this mass in the sun is encapsulated within a radius of around 700,000 kilometers. Now, the moon, which is a bit less extreme of a celestial body, has a mass of 10 to the 22 kilograms and a radius of roughly 2,000 kilometers. But if we were to turn all of those masses in the sun and in the moon into a black hole, the radius, the Schwarzschild radius of the event horizon would be only 3 kilometers and 0.1 millimeter, respectively. Now, I wanted to pause here for a second because this is absolutely mind-blowing. If we flash back to the original sizes, we'll see that all of this gigantic mass in the sun that was previously encapsulated by thousands of kilometers would only fit in a 3-kilometer radius now. So I hope it gives you an idea for how extreme black holes are. Now that we have that in mind, let me tell you what kinds of black holes we have in the observable universe. Well, they're divided into two main species, if you will. The solar mass black holes, which have the mass of a few solar masses. They are scattered all around our own galaxy, the Milky Way. And it is actually estimated that within our own galaxy, the Milky Way, we have roughly 10 to the 8 objects like these. So 1 followed by 8 zeros. I love spelling it out in the simulation, in the slides whenever I have the opportunity, because obviously astronomy is full of those ridiculous numbers. And the reason why we know these objects exist is because, as depicted by the artist's representation in the slide, they are mostly found in binary systems. So we know they exist because of the existence of the companion star. So these are solar mass black holes. Now there's the other kind, which is arguably more interesting. That's the supermassive black holes. And these have the masses of more than around 1 million solar masses, right? So that's 10 to the 30 times million, 10 to the 36 kilograms. And it is estimated that they reside at the centers of each observable galaxy in the universe, 1 per galaxy, or sometimes 2, but that's a discussion for a different moment. And since I wanted to be cheeky, I used a snapshot from the Interstellar movie. As much as I don't like the movie itself, I really like the black hole rendition of it, where you can see the Gargantua and this lonely planet and the starship next to it. So supermassive black holes are going to be the star of the rest of our show, because they are actually the ones that won the observational part of the Nobel Prize 2020 in physics. So I told you that we've got the solar mass and supermassive black holes, but how do you weigh those objects? Well, there are essentially 2 ways we can do that. And the question you may ask yourself is, first of all, black holes don't emit any radiation, right? They're black. How do you know? How can you know a mass of something that doesn't communicate with you through light? And second of all, how do you even measure anything in space, given that you don't have a scale that you can put under an object? Well, as I've said, there are 2 ways we can measure black hole masses, and if they're close enough to us, we can. Oh, now you're experiencing my beautiful graphics design, so do excuse my paint skills. But if the objects are close enough to us, we can track the motion of stars around the black hole in long enough times. And if we track their position and velocity, we are able to map out the gravitational potential responsible for all of those motions. And once we know the gravitational potential, we also know from simple dynamics and a little bit of general relativity, we can also infer the central mass responsible for putting all of that system in motion. So that's when objects are close enough to us. What about when they're further away, say 500 million years away from us? And when I say 500 million years away from us, I mean 500 million light years, because that's a measurement of distance. But since we observe the universe through light, I might as well speak time, right? So if objects are further away from us, what we do is, first of all, we can only look at the most massive black holes, supermassive black holes, and majority of them, if they're active, will be surrounded by an accretion disk, which I'm going to go into detail about in a moment. And above such a supermassive black hole, there is also a source of powerful X-ray radiation, we call the corona, that will send an X-ray signal directly to our telescope. Now, this X-ray corona does not only emit in one direction, so it will also emit towards the accretion disk. And as it does, this radiation will be reprocessed and sent back to us at a different wavelength. And when we compare the blue signal with the red signal, we are able to measure A, where the signal was emitted from, B, how fast the gas is moving in the accretion disk, see how turbulent that motion is. And given the position and velocity of gas in an accretion disk, we can again, just like in the case of stars, map out the gravitational potential and hence pin down the mass responsible for it. So that's how we measure those beasts, and the observed range of supermassive black hole masses is between 10 to the 6, a million, to 10 to the 10 billion solar masses. Actually, 10 to the 10 is very close to what the whole of our own Milky Way galaxy weighs if we were to add up the stars and gas within our galaxy. So these monstrous beasts span 4 orders of magnitude in mass, and yet they're so ubiquitous in the entire universe. That's absolutely mind-blowing. So before I move on to to the Nobel Prize, I also wanted to share a couple of fun science facts about supermassive black holes. First of all, they're not very dense. They are massive and compact enough, but not very dense in a sense, if we understand the density by its regular definition, i.e. mass within a volume. So if we take the volume enshrouded, encapsulated by the event horizon to be the volume of a black hole, and then divide the black hole mass by the volume, we realize that a 3 million solar mass black hole has an average density of water. And as a consequence of that, the gradient of the gravitational potential at the event horizon is very shallow. And what that means is you must have heard about spaghettification, which is the effect of strong gradients in gravitational field, which means that if you fall down through a black hole, say head first, your head will be pulled at your head will start falling at a higher rate than your feet are falling, and so you'll get stretched into a spaghetti. So nothing like that happens with a supermassive black hole, just because the gradient of the gravitational potential is so shallow. And in fact, if you look at the equation for an average density for a Schwarzschild black hole, you will see that the density falls off with the square of black hole mass, which means the more massive black hole, the less dense it is, the less likely you are as an astronaut to feel the passage through an event horizon. So we still don't know how supermassive black holes form, and that is one of the biggest puzzles that numerical simulations in cosmology try to answer with no success so far. And although paradoxically the black holes themselves do not emit light, we still see thousands or millions of them in the local universe. So at this point, I've told you a lot of fantastic stories along with the theme of our event. And you might ask, well, do they really exist? Am I not just pulling your leg? Well, there are at least 3 different proofs for the existence of black holes. And let me start with a fun one. I hope you'll be able to hear the sound in my presentation. So if you don't, that's a real shame, and please let me know. But first of all, we can hear black holes collide via the emission of gravitational waves. And let's hope I can play it for you. Did you hear that chirp? Well, I hope you did. I'll play it once again because I think it's fantastic. So wait for it. So this impressive event of 2 black holes colliding and sending ripples through space-time generates this. If you want to hear more sounds that black holes make when they collide, please go visit the LIGO website. Yet another recipient of the Nobel Prize. So we can hear black holes for their gravitational waves. We can also take a picture of their shadow. That's the newest addition to our collection of black hole proofs. What I'm showing you in the slide is a simulation of the light emitted from a weak accretion disk surrounding a supermassive black hole. And that's what it's supposed to look like. And that's a picture of it. So we cannot take a picture of a black hole itself because, as I said time and time again, they do not emit light. However, we can take a picture of all the right light around it, and then see the black hole itself because of the shadow, if you will, or the empty space in the image that it casts because of its own presence. If you want to know more, please visit the Event Horizon Telescope collaboration webpage. They have fantastic infographics and explanations of how this picture was taken and what it means to us. Oh, yeah. So the third proof brings me to the 2020 Nobel Prize in Physics, which was jointly awarded to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. So that's a theoretical part. And then the experimental part was split equally between Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. And let me stress out that the Nobel Prize Committee did not use the word black hole. They used the word compact object, because as much as we have a lot of convincing proof for the existence of black holes, since the Nobel Committee cannot really risk any technical slip, they still decided to go with a compact object as opposed to a black hole, since we do not have, if you will, a direct proof of its existence. Great. So if you want to learn more about the discovery, more than the quick overview I'll give you in a second, then please do visit the Nobel Prize Foundation official webpage. They've compiled a fantastic textbook summary of what black holes are and how the discovery came to be in a very accessible tone. So I strongly recommend that publication. Let me begin the discovery history of black holes with the fact that they are not as young a concept as we might think. Actually, it's just a bit over 100 years before Einstein came along that two interesting people, Pierre-Simon Laplace and John Mitchell, came up with the idea of dark stars. It's all in the Newtonian gravity, and they imagined a large star that was emitting light to an observer. But they hypothesized at this point, the speed of light was not determined, but it was speculated that it's not infinite, that it has a finite value, but the value was not known. But say there was a massive star emitting light to an observer, and it was massive enough for its gravitational escape velocity, as per Newtonian gravity, to be higher than the speed of light. In which case, the light, again, not good understanding of the nature of light, but say, in this case, the light would not be able to reach the observer because the escape velocity was higher than the speed of light. And so the light would have to return back to the emitting star. And in consequence, the star would appear dark. Now, this idea was simmering somewhere back in the bookshelf of history until Albert Einstein came along in 1915, formulating his general theory of relativity. And in the slide, I'm showing you a screenshot of the original publication that Einstein wrote. This is, until present day, a breakthrough theory that revolutionized our understanding of gravity, and it obviously came along with a lot of mathematical complexity. But only 3 months after that publication came Karl Schwarzschild, who solved Einstein's general relativistic equations in the trenches, assuming a spherical symmetry of the distribution of mass in the universe. Now, that's a real shame that in the May of 1916, Karl Schwarzschild died in those aforementioned trenches, which is a real shame because who knows what he could have achieved. But we have to fast forward to 1939 when Robert Oppenheimer, and together with his student Hartland Snyder, started pondering how an object described by Schwarzschild could come to be. And they decided that in the case of spherical symmetry, all the mass could collapse into a single point, and the object would lose its connection to the outside observers, i.e., it would no longer communicate. And of course, we know Robert Oppenheimer went to do slightly different things after 1939. And it so happens that I have the opportunity to talk to you from the very place where he decided to become the father of the atomic bomb, Los Alamos, New Mexico. So Oppenheimer decided to end his if you will, progress on understanding these weird objects called black holes. And then, which is good news, because then Roger Penrose came along in 1965, and for the first time in his breakthrough paper, he summarized the process of creation of a black hole, showing that for a general case of non-spherically symmetric distribution of matter, the matter would still collapse into a single point or a ring called a singularity, marked with a thick black line in the space-time diagram. And this singularity would be enshrouded in a mathematical boundary of no information return called the event horizon. Now, at this point, if there is anything from the story I would like you to take away, is the definition of what a black hole structurally is this point of infinite mass called the singularity, surrounded at some distance, in case of supermassive black holes, quite a far distance, surrounded by a mathematical boundary called the event horizon. It is not a physical boundary. You cannot put your foot on it, even if you got close enough. But it is the point of no return at which no signal can communicate out from a black hole with a distant observer. Now, this whole idea of singularity and an event horizon was then taken up by Stephen Hawking, whom we dearly miss, to extend it to singularities in the cosmological context and give rise to the Big Bang and the theory of evolution of the universe. But Roger Penrose was not really ahead of observations around this time. It was the other way around. He was more inspired by objects, exotic objects that we've seen in the universe. So the object I'm showing you right now is a quasar with a romantic name 3C273, which was identified as an extragalactic object, given how far it was and how much light it was emitting. Scientists have estimated it to hold roughly 10 to the 9 billion solar masses in a very compact area. So we knew, so at this point, the scientific community knew there are these exotic objects with very high mass. However, the exact distribution of this mass was very much unknown. And then several years later came Donald Lindebel and Martin Rees, who suggested that, first of all, every galaxy in the observable universe can host a massive dark object, massive dark compact objects like a black hole. And second of all, they proposed the observations which can be used to prove that these objects actually exist. And this finally brings us all to the observations that were awarded the Nobel Prize. And what the scientists wanted to do, they wanted to look at the center of our own Milky Way and track the motion of stars. If you remember my poorly made graphic, track the motion of stars to determine. Okay. Okie dokie. Sorry, I was trying to read the chat, but apparently I can't do two things at the same time, so I'll stop in a moment. But coming back. So they wanted to look at the center of the Milky Way and track the motion of stars. Now, the problem is that the center of our own Milky Way, if you ever get to see it up in the sky, is kind of covered in dust. Well, that's bad news, right? Because that's where we want to look. The circle is where we want to look. And all of this color is essentially dust. So the observations are really, really hard. And what Andrea and Reinhard did independently as it's a fantastic testimony to how science should be done. Two independent groups, two independent ideas, same result, cross-confirming each other, and then getting a Nobel Prize together. Spot on. So what they've done is they've used a clever way to take a series of short exposure images of the galactic center to avoid. Oh, I can hear someone. Can I ask everyone to mute themselves? I'm not as well versed as. Oh, fantastic! I can't hear anybody anymore. Great. So coming back, they've used a clever method to image the center of the galaxy at the wavelengths where the dust no longer interferes with our observations. And what they've done, they've mapped the velocity of stars at the very center of our galaxy, showing that it falls off as a square of the distance, with the square of the distance, which means the source of gravitational potential giving rise to all of those motions has to be compact enough to be treated as a point source. Now, and these two observations, the ones I'm showing you right now, these are the ones that got awarded the Nobel Prize. While fast forward to 2018, 3 years ago now, and with the use of proper general relativistic modeling and years of observations of position of star dubbed S2, we can now track the gravitational potential with general relativistic corrections, proving with no doubt that Sagittarius A star is our own supermassive black hole. And we can, thanks to Andrea's group, we can now even see a wonderful animation of how stars move in the center of our own Milky Way, with S2 marked with this beautiful yellow ellipse. So they've been awarded the Nobel Prize. You know what the black holes are. Time for the third, arguably most exciting part, was the big fuss. Well, let me ask you first what the brightest objects in the universe are. Actually, before I do that, let me read the chat. Oh. Okay, yeah. So I learned that that's some solid paint job. Thanks, Microsoft Paint for the win. And plate and spoon. That I don't think that was me. It could have been my dogs, though. So I do apologize about that. Coming back, I wanted to ask you what the brightest objects in the universe are. And I mean these objects. Well, they are nothing else than quasars. And quasars are essentially a fancy name for a supermassive black hole accreting matter at overwhelmingly high rates. I was looking for a good word, but obviously I lost it. So to give you an idea what the quasar that I mentioned before in the Nobel Prize part, of how out of this world this object is, 3C273 emits radiation 4 trillion times more luminous than our sun. And the total mass, as I mentioned before, roughly 1 billion solar masses inside. And this object is observed at a distance of just over 2 billion light years away from us. And yet still, it is an extremely bright point in the sky. And what is most shocking about it, I think, is that its variability timescale, i.e. the peaks and troughs in its emission, is on, they're only separated by roughly a couple of days. So on a Monday, it might be exploding at 4 trillion times the solar luminosity. And on a Wednesday, it might be 100 times less luminous than that. That is absolutely mind-blowing. And what the question is then, what makes the quasar so bright, given that I told you it's a supermassive black hole at the center, right? So the answer is accretion, which is the most efficient engine in the whole of the observable universe. So what I mean by this is you have a black hole, MS Paint for the win, and clouds of gas that are attracted gravitationally towards it. Because the black hole is likely spinning, the matter cannot just fall onto it and be consumed. It actually has to settle in an accretion disk in order to preserve angular momentum. Again, my paint skills are going to show off. So as the matter loses its gravitational potential, it heats up. And since it heats up to temperatures that are boiling hot, around 1,000,000 Kelvin or more, it emits a lot of radiation. That's exactly what the quasar is. You're not seeing the central black hole. You are seeing all of this hot accretion disk, boiling hot accretion disk at over 1,000,000 Kelvin, emitting light towards us in the full spectrum of observable wavelengths. And the efficiency of accretion, what I mean the efficiency, is how much energy is released given the total out of a gram of mass, where we use the conversion from the special relativistic conversion that everybody knows about, E = mc², right? So how much mass accreted by a black hole can be converted directly into this energy, and this is roughly 30%. And that is enormous, because if we compare it to other known energetic things like nuclear fusion, it's only around 7%. So accretion, these exotic, mathematically simple objects, black holes, they have the most capacity for harnessing power from matter as we know it in the observable universe. And if we add magnetic fields on top of that into this rotating black hole picture, so sorry, I'm not very good with animation. I probably would have killed that though if I tried. But if we add tangled magnetic fields that grab matter from this accretion disk, they can launch highly energetic particles around the pulse of rotation of a black hole, creating jets. So now that you know that black holes are dark, but also the brightest objects in the universe, let me show you what they look like. Here's a couple of quasars. This one is a single quasar that is being gravitationally lensed by a massive galaxy at the center. If you are interested in gravitational lensing, ask me at the end of the talk. So this is the same object, but we see it 4 times because it's gravitationally lensed. So that's what they look like from the top. And the reason why they're so useful, apart from all this interesting brightness, is because they allow us to investigate the invisible universe. And what I mean by this is that majority of our universe is filled with, loosely speaking, vacuum with some neutral gas. Well, not really neutral, but with gas. And if we have neutral gas in our line of sight, it is not going to emit radiation because it's not ionized, right? So the electrons cannot hop onto lower energy states because they're already in their ground state. Hence, there is no radiation emitted. The universe is dark. But if you use the light of a quasar, as demonstrated here by University College London, that is traveling through the universe towards us, through this neutral matter, as it travels, the light of a quasar will have all of the information about the neutral gas imprinted on its light signature. So from a clean spectrum, it will turn into the spectrum full of dips. And each dip that we've seen in the movie tells you about the presence of neutral gas. And if you track where the dips are and how deep they are, you can see what the distribution of matter is in the line of sight. So that's one way quasars are useful for us. So hence, black hole actually do matter. And if I can only change the slide, yes. The second reason why the fuss is justified is because they're fantastic general relativity testing laboratories. We didn't have that before Event Horizon Telescope, but now we do. So we can plug in full general relativistic treatment into our high-resolution numerical simulations to get an image like this. And then we can take a picture of the black hole shadow like this, like the one in the slide, the impressive space donut, and then compare the donut to the simulations in order to check whether it is consistent with gravitation, with general relativity or not. And as much as this image, unfortunately, is inconclusive, the Event Horizon Telescope team has another one, another image ready, well, in preparation for the next publication. And I strongly recommend looking out for their press releases, because it might be that general relativity does not stand this experimental test anymore. So finally, the last couple minutes, because I want you guys to have the opportunity to ask questions, I wanted to highlight that supermassive black holes are critical to galaxy evolution. So remember how I told you they can launch powerful jets, right? These jets are impressive. So my blue MS Paint cones correspond to these elongated structures. All of this is a total, well, is the light emitted by a galaxy. And as you can tell, this jet reaches far at distances higher or comparable to the size of the galaxy. In the case of M87, which, by the way, the donut picture is taken from. In the case of M87, the jets are even more extended. What you see with those red lobes and the blue streaks is a superposition of electromagnetic radiation at different wavelengths that shows you the historical, if you will, activity of the jet. So the galaxy itself is roughly this blob, which then is affected by this gigantic structure several times larger than the galaxy itself. Now, how does this compare to the quasars? Are these two different things? Is that the same thing? Well, I already told you with my schematic drawing that they're actually the same thing, but this was a big breakthrough in understanding black holes and accretion, that actually these two flavors of objects are the exact same physical process, but observed at a different angle. So a quasar would be you looking down the disk. So all you see is this very luminous accretion powered by the space-time donut. And if you look at the side, you will not be able to see the torus, really, because it's a torus in the accretion disk, because the galactic light is blocking it. But you'll be able to see the jet. So supermassive black holes they seem to be critical for galaxy evolution just because of the amount of light they emit and the spatial scale they can encompass, right? And to give you a flavor of what they can do is going through the cycles of bursty accretion and quiescence. They can, first of all, push out the gas out of the galaxy. And gas is vital for future star formation. No gas equals no stars. So if a given galaxy is deprived of gas, it will stop forming stars. It will become dimmer, redder, and eventually end up on the universe dumpster. These gigantic loops can also heat up the gas surrounding a galaxy, hence preventing future reaccretion of gas. If you want to know more about this, please ask me in the questions, because that's exactly what I'm working on. And as I've said before, all of these processes can ultimately lead to star formation shutting down, and hence galaxy dying in the long run. And as I've said, this is an area of active research. To be precise, my research? No, I'm kidding. It's actually a gigantic industry in astrophysics. So please do ask me about that if you're interested. Now, finally, I wanted to show you what this influence looks like in practice, because obviously I've shown you still images. The problem with astronomy is that we only do have access to the universe as we see it right now, right? It's very hard. It's just impossible, with the exception of a couple of nearby cases, to track the history of the evolution of the universe. I'm showing you a cosmological simulation from the Illustrious collaboration, which shows how new galaxies emerge from a web of cosmic over and under densities. And what you see here is galaxies forming in those bright centers. And in a moment, as they start evolving and we'll see a temperature map, now we're seeing a temperature map, you will see periodical, there you go, explosions of temperature around the galactic centers, or here as well. There's this nothing else than the supermassive black holes in action, blowing away gas, heating it up into insane temperatures, and creating this wonderful ionized soup of hot gas around the most massive galaxies. And when we look at still images of all of that, we will see that black holes, supermassive black holes, are not always active. They might be active like in the case of Cygnus, when we have the central galaxy, this tiny blob here, and these powerful radio jets being launched from the galactic center. But there are other cases, just much like our own Milky Way, this is the Andromeda galaxy, where the black hole is dormant. It doesn't have to accrete matter as long as there's no matter around it, right? So it will just peacefully sit at the center of Andromeda and not emit this powerful, monstrous jet. Similarly, in new galaxies being just formed, disordered, the black hole may not have had time to accrete a lot of matter around it and launch a powerful jet. Sometimes we'll also, actually majority of the times in the local universe, we'll see these boring, well, I like them, but boring, smooth distributions of light, which are dead galaxies. And since they have no gas, they also have no gas to fuel the supermassive black holes. So there are no jets, no quasars, and the galaxy is on its way to slowly die. And throughout all of these images, to show you how impressive the influence is, I wanted to tell you how massive the host galaxies actually are. So I told you that black holes weigh between 10 to the 6 and 10 to the 10 solar masses, while their hosts range between 10 to the 9 and 10 to the 13 solar masses. So this object, which is roughly 1,000 times, even more, 10,000 times less massive than the entire galaxy, is influencing its host at scales of hundreds of kiloparsec, where parsec is 3.26 light years, and a light year, I hope we can live with that. So finally, take-home points, and I won't bother you anymore. First of all, I want you to remember that black holes do exist, and we have observational proof for their existence, and they come in two flavors, supermassive and stellar mass black holes. Last year's Nobel Prize in physics was awarded to three people: Roger Penrose, Reinhard Genzel, and Andrea Ghez, for proving the theoretical and observational existence of black holes in the universe. And finally, I want you to remember that these beasts are not just sitting there being interesting theoretical objects, but also they have the power to influence their host galaxies, completely shutting down the star formation and causing galaxies to die. So at this point, I'll leave you with a map of a starry sky, except all of the points in this image are not stars. They're actually supermassive black holes in the local universe, as observed by LOFAR radio telescope. And there are roughly 25,000 supermassive black holes in this picture. So at this point, I would love to take questions, and I can read them right now. How is it? Okay. Okay. Manifold to Universe trilogy of Stephen Baxter is quite reasonable. Okay, wait. I got to the questions now. I'm sorry, it's just so much easier on YouTube. Okay, how far into science fiction, so to speak, should humans be able to harvest black hole power? Okay, nice. So harnessing black hole power is definitely in the realm of science fiction for sure. And when I mean black hole power, I definitely do not mean this. We're not able to do that. Actually, the more important question we should ask is it at all possible to extract energy from an object that seems to be consuming energy at all? Only consuming the energy. And that is, the answer is yes, we can. The thing is called the Penrose process. And spoiler alert, it's not technically feasible, even in the realm of theory, for us, for humans, to be able to extract the energy of a black hole. But still, it's interesting to ponder theoretically. So if you want to read up more, please check out what the Penrose process is, to see what I mean and what kind of efficiencies we can talk about here. Then we've got a question from Saville. And a question from Koto. When observing black holes, you said that we track X-rays sent out of black holes. How do scientists know they did not receive random rays? That's a fantastic question. So we do receive a lot of random X-ray radiation from the so-called X-ray background, and it's actually a combined. It is a combined effect of all the little X-ray emitting things like tiny black holes, supernova explosions that are surrounding us from all directions. If this were to be a random X-ray signal, we would measure it. Exactly the same at different points. Since we see that this X-ray signal comes from a single spot, say in the presentation. Let me come back. Okay, since we, for example, look at the center of M87 and see that the X-ray radiation comes exactly from a single point, and it's consistent in time. Yes, it does vary, but it is consistent in time and space over extended exposure times. We are certain that this comes from a black hole and not a random direction, because what we do to calibrate the instrument in the first place, we look at all the background around and measure its statistical variation. If the signal is above the statistical variation, we know it comes from the black hole. If it's not, it's just random X-rays, as you've asked. Finally, we've got a question from Savila again. How probable those images and renders are? What are the facts imagination ratio? All right, that's great. So facts, images, and I think the renders we were talking about are. I have to sprint all the way back to the beginning, and if I were more PowerPoint skilled, I would have done it smoothly. But hey, you have to bear with me. So here, how likely these renders are. So let's start with the solar mass black holes. Well, I would say to the best to the best of our theoretical knowledge, the render on the right-hand side is very little fiction, actually, because we know there is an accretion disk around the black hole. It's going to be hot, so we won't know its color, if it makes sense. It's too hot to be in the range of visible light, so we don't know if it's red or green or yellow. We can even call it purple. Any color you wish. It could be the accretion disk. We know that they do have companion stars, and we know that stars are roughly spherical, and we model in numerical simulations, we do model the mass transfer between an accretion disk and a star. So we do know it would roughly look like this. Would it be pretty to the eye? I don't think so. I don't think our eyes, even if we got this close to a solar mass black hole, that's not what we would see. We would see just blinding light that our eyes would not be able to take. So unfortunately, no chance here. As for the supermassive black hole, actually Interstellar did a fantastic job, and I want you to know that their simulation of the supermassive black hole light bending was actually real. It was done by real scientists on a supercomputer, and it was supervised by Kip Thorne. Of course, Hollywood has added some of its drama and confetti on top with all those additional highlights and shiny trinkets, but for the most part, this rendering in Interstellar is actually surprisingly accurate calculated using real general relativistic simulations. So this is very close to real life. And the question is, did I dislike the Interstellar movie purely based on how they present scientific data? No. I just did not enjoy the plot. I mean, hiccups are expected in sci-fi movies, right? I mean, I still went to watch Gravity with Sandra Bullock and the magical return of George Clooney because they obviously contracted him for several $1 million. But I enjoyed the movie. I just didn't like the Interstellar's plot. I loved the music. I loved Gargantua, but I didn't like the plot. Oh, and Matthew McConaughey acting, of course. Yeah, I forget about the main part. And Savile also asks, are we humans interested in black holes because they are there, or is there any actual influence? So I would arguably say that, first of all, is because they're there. And as I've said, they're the most mathematically simple objects we can imagine in the universe. And that already makes them relevant subjects for scientific study. But also, as I've said, they do have an immediate influence on galaxies, and understanding that is an important step in understanding how the universe evolves and where we came from. So, science for its entire history has always been interested in answering the question of where we come from and what are the physical laws that govern the universe. Well, black holes are a key ingredient in that evolution. So as much as they don't have an influence for our day-to-day life, they actually do have influence on our understanding of the universe. And one more thing, actually. I remember I told you about X-rays and how we observe them, how we observe the X-ray signature. Well, in order to do that, astronomers had to design special CCDs, special camera capturing devices to be able to capture the X-rays. And these CCDs were then moved into the medical industry. So right now, when you get an X-ray, think of it as a machine that was first designed to look at massive black holes. So I think that's all. And if there are no more questions, I think we can end it here. Also, if you end up having any more questions after that, if I can only skip to the beginning slide, you can find me here. So I hope you enjoyed a little bit about black holes, and I shall hopefully be in touch with everyone interested. Woo! And the clapping, thank you. Oh, this is the worst thing about online talks. You never hear that.
It was lovely.
Thank you. I hope you guys liked it. All right, awesome. So I shall leave the room right now. Is that okay?
It's absolutely brilliant. Thank you. Bye.
Bye.